In this exercise, we will use linear regression on a larger dataset and a more realistic example. We're going also to learn about feature selection using the lasso model. We're going to import the needed packages, and we have here a helper function to calculate the adjusted R-square. In short, the adjusted R-square score for a regression model is based on the R-square score, but it adjusts for the number of variables in the model. The more variables we have in the model, naturally the R-score will rise up. So the adjusted R-score discounts depending on how many variables we have in the model. This helps us compare models that have different number of variables. So when we add new variables to the model, are we gaining more in terms of prediction? The adjusted R-square score helps us to make that determination. In this example, we will examine a dataset used often in many data mining examples called the Toyota Corolla dataset. In short, this dataset has historical pricing of used Toyota Corolla cars. So the outcome variable, the dependent variable that we would like to predict is the price of the car. Think about using this data to improve in a car dealership, for instance, or vice versa, used by customers in order to price their own cars. Now, this dataset has many more variables, many features, which are basically, strictly speaking, the features of these cars. And let's read the data here. And here is just one column in the data. If we take a look at all of the columns this data has, you can see that it has a large number of these features. So obviously the ID and the model, but then the price, the age of the car. Let's take a look at how many of these columns we have. We have 39 columns, so excluding ID, model, and price, we get 36 variables, and some of these variables are also categorical. So when we convert them to dummy variables, we will have even more features in our data. And now we can run a regression model on all of the variables we have. But there are two dangers here. One danger is, if we're using this model for explanation, there's simply speaking too many things going on, and this defeats the purpose of creating a parsimonious model. Say you would like to explain what leads to a better sale price of the car. When you include all of these variables in the model, it will become even harder to make such an explanation. Danger number two, if we're using it for prediction purposes, including many of these variables in the model, risk overfitting the model to the data. And while we can mitigate overfitting with split train test, so that we don't overfit to all of the observations we have, we still have so many parameters when we're training the model. And then we run into the curse of dimensionality. The performance of the model will be, simply speaking, weaker, simply because we have so many things we're trying to adjust the model to fit to. So we would like to be more strategic. We would like to select variables that make more sense. And there are two approaches to do this selection. One approach is by doing manual feature selection. And manual feature selection basically reflects in a way to the experience of the data modeler, sometimes the domain knowledge. If you have access to domain experts, you may ask, which one of these variables makes sense? For instance, let's say you can speak to people who work in the car sale industry. Which one should I include? Which one should I not include in my model? That's approach number one. And approach number one, in addition to manual selection, there is also manual exploration. Simply speaking, you may want to run many models with different feature selections and compare and contrast the performance of the model. Approach number two is basically to systemize and automate this process of feature selection. And there are many ways to automate this selection. In this exercise, we will learn about a model called Lasso, which under the hood runs a linear regression and also do feature selection using regularization. So while we're not going to talk about the technical details underlying the model, and I link to the page here, you can check, read more information about the lasso model. Conceptually speaking, what the model is doing feature selection in addition to linear regression. So what we're going to do in this exercise, we're going to use first simple linear regression on a subset of the features. We're not going to try everything. We're just going to try a subset of the features and see how well it performs on both the training and testing subsets. And then we're going to perform a lasso regression on the same data and examine the difference in the results. And finally, we're going to perform a lasso regression using all predictors. Okay, so let's take a look at what we have here. First question is asking us to predict the price of the car on a subset of these variables. So what I'm going to do here, I'm going to take these variables or features here, and let's call them predictors, and put them in a list. Then the outcome variable is basically the price of the car. Now the next step is to basically pull the x and y's from our data. So the x is our data of the predictors, and the y is our data of the outcome. Now the subsequent step is then to split the data to test training sets. So I'm going to use the function split train test split here. So here's the code. It will generate the training, the x for the training, the x for testing, the y for training, and the y for testing. And I have determined the test size to be 40% of the total data. And I started from a random state of 1 because I would like to use the same testing, the same splitting in the remaining of the questions. So once I have my data, then I can start and create my linear model. So I'm going to create a linear regression model. Now I can set intercept to be equal to true, which I believe would be the default value anyhow. And then I'm going to use the model, train the model to fit train X and train Y. Now the problem here is that some of these variables are categorical. So before being able to run the model on categorical variables, I have to create dummy variables. So here in this step, if you take a look, let's actually do it in, to show you the issue here is that some of these variables are categorical variables. So one way to convert these categorical variables to numerical variables is to use the function getDummies. When you get dummies, you get multiple variables for each categorical variable. For instance, fuel type will now be 2 variables or 3 variables. Fuel type CNG, fuel type diesel, and fuel type petrol. Now, because of each observation may be only one of these variables, I can drop the first variable, because if it's not CNG, it will be either diesel or petrol and vice versa. So I'm going to drop first equals to true here. Okay, so actually this should be my x. So my x should be this one, just converting all of the categorical variables to numerical variables. And now I guess I can go proceed, do the splitting, do the training, and I have my linear model trained. Next step is to report the model. So I'm going to print the intercept and I'm going to print the coefficients. So here are the coefficients of the model, and many of them make sense, you know, age and kilometer of the car. Some of them are a bit interesting to look at, but we are now, so you should be able to look at these coefficients, and for explanation purposes, look at these coefficients and say, okay, with each extra kilometer the car makes, the price is reduced by 1 cent, 1.6 cents. So that makes sense. For instance, the weight of the car increases the average price of the car, so that's interesting. Automatic cars sells for much more than manual cars, and so on and so forth. Okay, next we're going to evaluate the model, and we're going to make this evaluation using the training data, and then we're going to see if the model overfitted the data by re-evaluating it using the testing data. So what I have here, I have basically making a prediction using train X, and then I'm calculating the R-square score in between the training of X and the predicted values, the original values and the predicted values, and I'm also calculating the adjusted R-square. And you can see that both of them are almost around 88%, 87%, let's say, which is great. That explains 87% of the variance around the variable price, leaving only around 13% of unexplained variance. So it looks like the model is doing great. But we shouldn't make a leap to such conclusion, because at the end of the day, we want to make that on new data, data that the model hasn't seen. So let's replace here train with valid. That's the holdout data, and repeat the same, and this one should be valid y, the same comparison again. And lo and behold, you can see that the R-square now drops to 10%, and the adjusted R-square score now drops to 8.5%. So the model is not doing great. It only explains 10% of the data that it hasn't seen, indicating a serious overfitting, even with train test split. So the next step to improve on the model is to do feature selection. And again, as I said, you may want to do this kind of semi-automatically. Maybe you want to take some of these that don't make sense. Let's say, for instance, a domain expert tells you, well, doors doesn't make sense, the number of doors in the car as well as quarterly tax. So probably you take out this feature and you run the code again. And you can see that the model has improved substantially here. It seems that some of these features here are completely not needed. And I have taken the doors and the tags, after having run the lasso model, and just realized that they're not really needed. But that's something you can do either by exploration or by talking to people who are domain experts. Let's do this automatically using the lasso model. Now, the lasso regression model does two things: linear regression and feature selection using regularization. So everything else should be the same, except that instead of using a linear regression, I'm going to use a lasso model here. So I'm going actually to take this code. Well, indeed, I don't need the whole code. I just need this code here. And let's type it in here. So let's do it using the lasso. That's question number 2. I'm going to create a model called lasso here. And I'm going to supply some of the hyperparameters of this model. The next step is to basically the same, lasso.fit train X and train Y. That's going to fit the lasso model. So how is it any different from the linear regression model? Well, let's take a look. I'm going here to do the printing, but I'm going to print the coefficients of the lasso model. So instead of car-lm, obviously I should put lasso here. And probably this piece of code should be isolated in a function because I'm copying and pasting all over the place. And you can see that the lasso model decided that, you know what, the metal color is not really needed. I'm going to drop this feature. The doors is not really needed. I'm going to drop this feature. So indeed, it actually decided to drop door and met color in its process of feature selection. So simply speaking, dropping these two features results in a better model for explanation purposes because you have less things to interpret. If you're interpreting this in the previous model, what would you say, for instance? Let's do this. Okay. You'd explain to someone that each extra door increases the average price of the car by $58. Okay, that's interesting, but I mean, probably not true, because maybe this is the outcome of, something else being related to the number of doors. At the end of the day, Toyota Corollas all have 4 doors, 5 doors. What does it mean? And does it mean if we have a Corolla with 7 doors, it will sell with even more? That seemed to be a kind of an artifact of the data rather than a true hidden pattern. An interesting insight here. Okay, so let's evaluate the performance, and I'm going to use the same code here. Again, probably it makes sense to isolate it. I'm copying and pasting for now, so you'd excuse me, and should make sure I'm not making a mistake. So the lasso model, when it's being tested on the same training data, it's basically resulting in similar performance, almost 87%, 86% to the linear regression. But if we do this, and once again, I should rerun this number for the linear regression. That's the linear regression with the original set of variables. For the lasso model here, we get to 80%. Meaning here we are avoiding overfitting the data because of the inclusion of extra features. So this is great, because now when we are trying to, when the model is being tested on data that it hasn't seen, understandably it does less well than when it is tested on data that it has seen, but not in a dramatic fashion. I mean, it's a difference of 6% between 86 to 80%. So that's kind of an almost a drop of like 7% in performance. But 80% is still good here, and the difference is not that big. So now, armed with our knowledge of the lasso model, we can even do better, because we have a large number of features here that we can use. So instead of using just a bunch of them, probably 10 or 11 features, I'm going to use all of them. So here's what I'm going to do. I'm going to copy the code again here. And my outcome should be the same as price. That's the same. However, my predictors, what I'm going to do here, I'm going to grab all of the columns and I'm going to exclude outcome, as well as the sum of ones that obviously don't make any sense, such as ID and model. I mean, who cares about the name of the car here? We can do some text mining, but that's basically the name of the car is incorporated. All data here is reflected in all of the variables. So I'm going to exclude ID, model, and price. So price is outcome, and then ID, and then model here. So obviously we can do a linear regression here. I'm going to kind of ignore this step for now. We're going to use lasso. Feel free to run a linear regression and compare and contrast with the lasso, and you'll be surprised how well the lasso is avoiding the overfitting problem. So I'm going to use the same code here. I'm going to create a lasso model and training using the train X and the train Y. I forgot to, let's see, x column has to be set here. So that's x.column taking out the set of outcome ID models. And probably I made a mistake here. Fuel is not in the index. It's not x.column, it's basically data.column, the original data, not the transformed x. Okay. So data.columns, taking out outcome ID and model, and then we are training the lasso model. And let's now see how it performs on the training data. 90%, 90% even when adjusted, so that's really good, but we shouldn't celebrate because we know this is a data that the model has seen. How about data that the model hasn't seen? Well, it's 88%. 8 is almost 88, 87% when adjusted. So that's great, because with all of these variables, we can almost predict 90% of variance in the price of the car, leaving only 10% as, resulting in, as a result of some unknown features or just some internal randomness and fluctuation in the process itself. Let's take a look at the coefficients here. And what I'm going to put in here, I'm going to take a look at these. And you can see that the lasso decided that many of them do not make sense, excluded them, including the number of cylinders, whether the car has a radio cassette, MFG month, metal color, the mist lamps, backseat dividers. It also did feature selection. So that's useful because we can take a look at this feature and we can say, okay, many of these features are not important. Gears, for instance. Color itself, many colors are not important, but one particular color is some of these colors are important. So that's interesting. Probably some people have strong preference towards certain color or strong kind of dislike to some colors, but some of the colors are completely neutral. Probably there are not many cars with these colors. I don't know. Violet, Toyota Corolla, I haven't seen one. Fuel type is also excluded, so on and so forth. So now we have a model which is good for explanation purposes, because we can now be more confident when we explain these coefficients, but also does a decent job predicting the price of these cars.